Okay, so question 4 is Big Bang and astronomy. So the Big Bang is one theory for the origin of the universe, and this suggests it had a beginning and it's still expanding. Which of these provides evidence that the universe had a beginning? The discovery of other galaxies? No, but they helped us tell that the expansion was increasing in the velocity. The discovery of Jupiter's moons? No. Discovery of planets? No. Cosmic background radiation. As I said to you guys, that is the photograph of your great, and say it for a long, long period of time. Grandad, that's where we all came from. And we have a photo of it. So evidence that the universe is still expanding comes from observations of light from distant galaxies. Describe how this shows us that the universe is still expanding. Well, it doesn't just show us it's still expanding. It tells us that it's also expanding at an ever-increasing rate. So we looked at Hubble's law, and we saw that the greater the distance the galaxy with us, the greater its recession velocity. And we measure this using redshift. So the basic idea is that galaxies that are further away from us, they're moving away and their wavelengths get stretched, so they become more red. We end up with redshift. And the crucial part is the bit greater the distance away, the greater their redshift, so the greater their velocity. So I don't think we need to mention in this, we just got to just say, how does it show that they're expanding? So light from distant galaxies has been redshifted, that's a mark. Then we've got to explain, well, this just means that the wavelengths have been stretched out, or the wavelength has increased. So the light has a longer wavelength as that light has been stretched. This shows that the galaxies are moving away from us. That's it. And we don't need to mention that it's faster the further the way. The steady state theory is also a theory about the origin of the universe. Give one similarity and one difference. So there's a little picture of it. So steady state cosmology states that the universe is expanding, but as it expands, it creates new matter in between. The Big Bang cosmology is that all of the matter started from an intensely hot and intensely dense starting point, and then it's expanding outwards and diluting over time. So there's the basic ideas, but we can now go through how they're the same, how are they different. So both have an expanding universe. 1 mark. And the next one, the difference is steady state has no beginning and matter is continually forming as the universe expands. Or I could say the Big Bang theory, the matter is created in the Big Bang and is being diluted as the universe expands. Okay, next one, we've got observations of the universe, and we've got the distance in megaparsecs on the bottom, and we've got the velocity in kilometers per second on the side. And it's going to ask us, use the graph to estimate the velocity at 15 megaparsecs. So arrow up, arrow across. We can see where our line intercepts. Each of these mini squares is 50, so that's going to be 1050 kilometers per second. Next one, calculate the gradient. So we want to calculate the gradient of this line. Well, we can just use the data that we've just worked out on the graph, and we know that the gradient equals delta y divided by delta x. Change in y, this, divided by that. So now we can just pull out the values. So 1050 divided by 15 equals 70. That's going to get us a mark. That's getting us a mark there for the calculations. And then it wants the units, and we can see that we've got y is kilometers per second. That's on top. We've got megaparsecs underneath, and then we've just got the division line in between. So then we just need to write that as kilometers per second per megaparsec. Done. The next one is, why does it only provide an estimate? And I've left the answers in here rather than animating them, because I'm going to flick backwards and forwards between the two. So why is it only an estimate? Well, the first part is the data points are scattered widely, and we can see that on that graph. If I go back to this here, we can see we've got the data is scattered. So I could equally have drawn a line of best fit here. I could equally have drawn a line of best fit here. So let's imagine now one more comes in, it goes there. It's going to massively change the line of best fit. I discover another one, it's over here, it's going to change it again. So we can see, and we don't have that much data in that graph either. So the data points are scattered widely about around the line of best fit. So there's a mark for saying the data scattered, and therefore there are lots of different gradients or many lines of best fit that could be used. And that's that question done.